Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on reaction kinetics. So this is topic 26 for the CIE specification, so that's the Cambridge Internationals. So if you're studying the CIE specification, the syllabus, then this video is perfect for you. In fact, this is just obviously topic 26. There's the full range of year 1 and year 2 videos are available on Allery Chemistry YouTube channel. Just hit the subscribe button to show your support for this project. That'll be massively helpful. These videos as well, they're made from slides, PowerPoint slides, which are available to purchase via my test shop. If you click on the link in the description box below, you'll be able to get a hold of them there. They're great for supplementing your other revision material that you may have, you know, your books, your notes, etc. And obviously you can print these off and write your notes next to them if you wish. So yeah, so obviously this video we're going to go through reaction kinetics. So obviously this is to do with rates of reaction. So we're going to look at the first part, which is rate and collision theory. And actually, just before I go through this, you'll find that a lot of the kind of topics kind of overlap within the CIE. So there's a lot of bridging between other topics that have gone before. Now, clearly, this is for the year 2 specification. There is an equivalent topic with the same name called reaction kinetics in year 1. So obviously this video relies on the fact that you've watched that or you understand the basic concepts of kinetics and obviously rates of reaction. This obviously builds up on that as well. So if you're not too sure or your kind of knowledge is a little bit rocky on kinetics, I encourage you to go and watch the year 1 video first, or kind of, you know, brush your knowledge up on that, and then obviously watch this, and then it might make a little bit more sense once you're looking at this. So, okay, so let's look at rate and collision theory. So this is a little bit of a kind of acknowledgement from year 1, and you should understand this from year 1 anyway, but it's good to kind of just overlap slightly. So for a reaction to occur, obviously particles must collide. Now, rate of reaction is effectively the change of concentration or the amount of a reactant or product per unit time. So that unit time could be minute, could be seconds, it could be, you know, anything like that. So you've really got to look out for that, because there could be, you know, it could change. So the equation is rate equals the rate of reactant used or product made. It could be either, divided by time. Now, you've got to remember this equation. You're going to see it all the way through this topic and all the way through year 1. It's probably one of the most fundamental equations in relation to kinetics that you'll see. Okay, so obviously particles are moving all of the time. Okay, so there isn't any part of a particle where it doesn't move at all. So they're all moving all the time, and they do collide into each other quite often, actually, but most of these collisions don't lead to a reaction. So a lot of them will just bump into each other, and they'll just kind of bounce straight back off. Now, for a reaction to actually occur, we need the particles to collide in the right direction, so the right orientation. So they can't just be colliding from one particular place. Obviously, the functional groups, which you would have seen in year 1 organic chemistry, the functional groups have got to align in a particular way. You know, so the orientation is obviously quite important. The other one as well, which is probably just as important, mainly to do with the physical side of it, is they've got to have the right amount of energy, the amount of kinetic energy for them to actually react in the first place. So a lot of particles, in fact most of them, will kind of bump into each other, but they have nowhere near enough energy for them to actually generate a reaction. They'll just bounce off each other. But if the particles are hitting at each other at the right speed, and if there's enough energy for that reaction to happen, then we will get a reaction. Okay, but like I say, most particles collide and they don't actually react. So that's the vast majority. So obviously this is looking at a particle theory, so like a particulate level. Obviously we've got to measure rate experimentally. Scientists have got to look at different reactions and how do we actually measure and monitor the rate of reaction, how a reaction is actually proceeding. So there's loads of different ways, and it really depends on the reaction that you're doing. But I'm going to go through a few here just to kind of acknowledge that. And again, you would have seen this in year one. But during a reaction, there may be a change in the number of ions. You may have more ions that are produced compared to the reactants. And them ions will, if they're free moving, then obviously they will allow a conduction of electricity. And obviously the change in the amount of ions that's now available as the reaction proceeds will change the level of electrical conductivity. So you don't really get many experiments, I suppose, like that, and you might not have seen it in the lab, but nonetheless it's a method of measuring rate of reaction. A probably more common one is amount of mass lost. So for example, for reactions that produce a gas, then we can put the beaker, as we can see here, we put the beaker on a top pan balance, and obviously this will measure mass loss. So obviously you set the reaction to where the gas will escape out of the conical flask, and obviously we can measure the mass over time and record down the different masses at particular intervals. A fairly accurate method does have its downsides though. Obviously, if the gas is toxic, you don't want to breathe that in, so you might need to use a fume cupboard. It just depends on what the reaction is. Probably a better way of dealing with that is another one, which is probably a probably more common way of doing it, probably than even that one that we just talked about there, is measuring the volume of gas that's produced. And we can do that by using a gas syringe. So effectively it's a similar system where you have your reaction and you have a gas that's produced. This can go up through a delivery tube into a gas syringe. And then what we can do is we can measure over time how much gas is produced over time. Now obviously this is obviously going to measure rate, because you can say, right, how much gas have I produced in, say, 30 seconds, in a minute, in 1 minute 30, etc. So you've got various different methods then which you can measure rate, and there are others as well. Obviously this is just looking at one. You might have one where you might get a color change, for example. That might be another one whereby you might have seen it with thiosulfate reactions. So we'll call it a disappearing cross reaction, where you have your beaker and obviously it goes cloudy depending on the changes in concentration, and then you have a cross underneath it, and you're basically measuring the time it takes for that cross to disappear. And obviously the time will be dependent on the concentration of the reactants that you're using. So there's loads of different ways you measure rate. I'm just putting a flavour on here, I suppose. The concept though is the same, and really the topic focuses on what can we do with the data that we've got, and how can we then use that to comment and discuss and calculate rates of reaction. So another one is obviously changing pH. So obviously pH of a reaction may change over time. So if H plus ions are used up or they're produced, we can monitor the pH of that. And obviously we can use a pH meter to monitor the change in pH over time. Generally, this can be for something. It might be like a titration, for example. There we are. There's your titration. So obviously, we can monitor the change in concentration of a reactant or product. So what we do is we take small samples, or we call it an aliquot. That's the official name. You might not have heard of that before, but if you have, then you're probably in the minority. So you take an aliquot of at regular intervals and you titrate them. So basically you set a reaction away, it starts reacting over time, and maybe it's every 30 seconds or every 10 seconds, however quick the reaction's going. You basically take a sample of that. So you put your pipette in, take your sample out of the reaction vessel, and then you basically, because it'll still react in the actual pipette that you've drawn that liquid up, you've got to add it to a quenching reagent, and that will basically stop or freeze the reaction at that point. Now, depending on what you're reacting, and will depend on what the quenching reagent is. So what we're going to do is when we add it to the quenching reagent, then we basically then titrate it against, say, if it was an acid or an alkali, we can titrate it against that and monitor the concentration of how much of the product have we actually got, or even reactant, how much have we got in that reaction vessel at that particular moment in time. And obviously by running a titration, we can work out, how much of the titrate we need to react with whatever's in that beaker. And obviously, if we take samples of the reaction vessel over a period of time, hopefully the amount of reactant or product will change during that time period, and we can monitor how much of each, either the reactant or product. Again, it really depends on what you're measuring here. We can monitor that by titrating it, and then obviously we can write down the titer values, and obviously that can then be used to monitor the rate of reaction. Okay, so really important. So there's quite a few ways in which we can, obviously experimentally, in where we can measure the rate of reaction. Okay, so we've got some data then. Let's kind of move away from the experimental side and say, right, well, we've got the data, we need to record it somewhere. So you record it in a table or you plot it on a graph, etc. And you're going to see a lot of this throughout the video. So here we're going to look at some graphs first, and obviously rate can be found by obviously calculating the gradient of a graph, as you can probably see here. So the gradient is change in y over change in x. So y is obviously the vertical axis, the horizontal is obviously the x-axis here, and obviously when you're looking at this, it's good practice to use a big section of the graph here. So obviously the bigger the section of the graph you use, the better for working out the gradient. Now what we want to try and do is find points where it's easy to read. So in other words, don't go for something like here, where it's kind of using halfway through one of the squares and then you're having to kind of guess what that number is. Try and make it easy for yourself and look for points where it kind of hits nicely on one, and maybe it hits nicely on the other axis as well. It just makes it a bit easier. So let's have a look. So I've drawn some ones here. So we're going to measure the rate of reaction here. So the difference is 6 on the bottom here, and the difference here is 4. So the change in y is 4 divided by 6. There we are. And that gives us 0.67 centimeters cubed per minute. Now the reason why we know it's these units here is because we're measuring the volume of gas in centimeters cubed, and the time frame is per minute. So look at the units on the graph to give you the units of rate that you've worked out. So obviously this is the rate of reaction for this particular reaction. Now, it gets a little bit more difficult when, obviously, you don't have a straight line graph. You've got a curve instead, which, again, you'll see a few more of these later on in the video. But obviously, with a curve, and if you do maths, or you study maths, then this might be a bit more familiar with you. But if you've got a curve, you've got to find a tangent. And a tangent is basically a diagonal line that meets the curve at a specific point that you wish to view. So the best thing to do is extend the line right across the graph, work out the gradient, as we mentioned before, and then obviously we're looking to monitor the rate of reaction at a particular point on that curve. So here we're going to work out what was the rate of reaction at 3 minutes. So we're going to draw our tangent at 3 minutes, and you can see here at the 3rd minute, the tangent is pretty much parallel with the curve at this point, and that's what we're trying to aim for there, and extend that tangent right out as big as you can get, because that's how you're going to get a more accurate reading. So gradient, again, it's just exactly the same from now on. It's change in y over change in x. So your change in y is 0.8 and your change in x is 4. So we put them figures into there and we get a gradient of 0.20 grams per minute. So again, look at the units. We've got grams on the left, minutes on the bottom there. Okay, so it's a different set of units, but it's still telling us about the same thing. Okay, so this is the rate at which this was moving at. Okay, so we're now going to kind of step a little bit further. This is where the kind of year 2 stuff comes in. A lot of that stuff you should have kind of seen through year 1, and you should understand how you work out a rate equation. How you work out rate from a graph. Here, we're now going to kind of take it a little bit further, and we're going to look at the rate equation and orders. Okay, so rate equation, all the rate equation does, it links rate with concentrations of substances. So the rate equation is rate equals K, concentration of A, and then the power of it, and concentration of B and the power of it. So you've got to remember this. We're going to see a lot of these. We're going to look at loads of different reactions using this equation here. So there you go. So rate is in moles per decimeters cubed per second. This is the rate constant, and obviously the units can vary. Obviously they have to be worked out. And this is the concentration of a substance. So it follows obviously the equation in this format. So you've got A plus B will produce C plus D. So this is what obviously the letters mean here. The little subscripts, or superscripts should I say at the top, are the orders of reaction, which we'll come on to in a moment. So orders of reaction is basically the power to which the concentration is raised to in the rate equation, as we can see there. And it basically tells us how the concentration of the substance affects the rate. So in other words, if we change the concentration of a reactant, for example, what impact would it have on the rate? And some reactants will have no impact at all, and some will have quite a significant impact. And obviously the power is just trying to measure the impact that that reactant could have. So for example, if you have something that has 0 order, then any changes in concentration of that substance will have no effect on rate. So for example, if the concentration of A doubles, then rate doesn't change. So if you're in industry and you're looking to speed up the rate of reaction, then you changing the concentration of A will have no impact. So you wouldn't bother with it. You just leave it. First order, this obviously changes in concentration is proportional to the change in rate. So for example, if the concentration of A doubles, then the rate doubles. Okay, so that increases. So it's basically proportional to. And then second order is changes in concentration has a squared proportional change on rate. So for example, if I double A, then the rate will quadruple. Okay, so we're looking at how this obviously affects that completely. Now, orders can only be determined by experiment. You can't just look at the equation, okay, and say, that's first order, that's second order, that's 0 order. You can't do that. We must use an experiment. We've got to use experiments to work out what these are. And you'll see later on when we come to a table of data and you get loads of different experiments that have been run, the exam board will be wanting you to use this data to work out what orders are. You cannot just look at a reaction, a chemical reaction, and just say, right, it's going to be, just like this here, and say which one's first, which one's second order, and which one's 0, or if any. Okay, so really important. But we'll look at some data anyway to help you work this out. Okay, so the rate equation, this obviously links rate with concentrations of substances. That's what we've just seen before. Okay, so the rate constant, which was K, is a number that allows us to equate the rate and concentrations of these substances together. So the rate constant is only fixed at a particular temperature. Okay, so it depends on what the temperature is. If the temperature changes, so does the rate constant. Okay, so K increases when the temperature increases. Okay, so that's really important. So that can change. And the larger the value of K, the faster the rate of reaction. So these are all kind of relationships that you need to know. So let's have a look at the explanation. So if we increase the temperature, okay, the particles have a lot more kinetic energy. We've seen this in year 1. And obviously this increases the rate of reaction. So if we increase the temperature, we know that rate will definitely increase at this point. But the concentrations of these, we haven't changed them. When we heat a reaction up, we're not changing the concentrations of these at all. Okay, so these will just remain the same. So this equal sign tells us that the value here must be the equivalent to the value here. Now, if this is increasing and this is remaining the same, then to keep both proportionate and equal to each other, then obviously K has got to increase. It's got to keep this balance here. So this is the reason why we can say that actually, if the temperature increases, then the rate increases. If the rate increases, then K must increase because we're not altering the concentrations at all. So this is how we can kind of explain this relationship between them. Just be aware of that because that could be quite important if they ask you questions on it. Okay, So, rate can be calculated using this rate equation. So we're going to now use this now and actually do something with it. So we've got a reaction here, and this was carried out in the lab, and we've got 2 lots of nitrogen monoxide, so 2 lots of NO, reacting with oxygen to form nitrogen dioxide. So it was found that actually this reaction is second order with respect to NO, and it's first order with respect to O2. And we're going to calculate the rate of reaction given the concentration of NO is 3 times 10 to the minus 3 and O2 is 1 times 10 to the minus 3. The rate constant K is 700,000 moles to the minus 2 dm6 s to the minus 1. So we've got a lot of information there, and we're going to use that rate equation that we'd seen before. So we need to write the rate expression first. Really important. If you're faced with a question like this, substitute the reagents that we've got into a rate expression. So here we've got rate equals K NO squared. Okay, so these are obviously your reactants, and O2 to the power of 1. Now, essentially, obviously, I know you probably got some people who study maths in what you're doing that for, what you're putting the 1 there. I'm just putting the 1 there just to show that actually there is a number there. For those who don't do maths, there is a number there, and this is basically to the power of 1. But ultimately, you can just omit that. You don't have to have that number there. And just the square bracket and O2, obviously, there must be something there. So this 1 is just basically just for clarity purposes. So we're going to put the numbers into the rate equation. So we know that K is 700,000. We know that NO is 3 times 10 to the minus 3 squared. Okay, so we know it's second order. There we are. Second order with respect to NO. So that's why it's got the 2 there. Okay, so it's squared. Times by 1 times 10 to the minus 3. And obviously this is first order with respect to O2. So it's just first order. The rate is then 6.3 times by 10 to the minus 3 moles per decimeters cubed per second. Okay, so that's the rate of reaction. Relatively straightforward. It does get a bit more difficult than this. Okay, but it's a start. Okay, so the first thing we need to find out what the orders of reaction are, and that's your powers that go on the top there. Just so happens to match these as well, but the orders of reaction is we can only find that out from experiments. So they've either got to tell you it, or they've got to give you data to work that out. Obviously, K, we know what that is, and we've worked out rate. Okay, so calculating rate constants. So your rate constant can be calculated from the rate equation 2. So we're going to look at this reaction here. Okay, so this is a slightly different reaction to what we've seen before. So we've got nitrogen monoxide reacting with carbon monoxide and oxygen, and that will form nitrogen dioxide and carbon dioxide. Now we're going to calculate the rate constant for this reaction. Now we've been told that the order with respect to NO is second order, and 0 order with respect to CO and O2. Okay, so there's 0 order with respect to them. The concentration of all reactants is the same, so it's 1.5 times 10 to the minus 3 moles per dm cubed. Rate of reaction is 1.17 times by 10 to the minus 3 moles per decimeters cubed. So we write out the rate expression. Now you'll notice here that we put NO squared because we were told that NO is second order, but we've omitted carbon monoxide and oxygen. And the reason why we don't write that in the rate equation is it's 0 order. It doesn't have any impact. So we're only including reagents in here, and you'll see this when we do multi-step reactions later on. But in the rate equation, we only include reagents which affect rate. Okay, which have an order. If it's not in the rate equation, it cannot impact the rate of reaction. Okay, and you'll see that again when we do multi-step reactions, and we'll do rate determinant step and things like this later on. That point that I just kind of said there is really important. I will emphasize it again later on. So to rearrange, we need to obviously make K the subject. So K is rate divided by NO squared. And then it's quite simply, it's the easy bit now. We just put the numbers in. There's your numbers there. And we get K is 520. Now remember, the units of K can change. Okay, and it's dependent on the reagents that we've got here. So we've got a rate which is 1.17 times by 10 to the minus 3. That's moles per decimeters cubed per second. And then we've got a concentration here, which is moles per decimeters cubed, but it's squared, as you can see on there. So we're going to work out the units, and we've done this before. You've seen this in previous topics where we work out units, but we're going to basically just write the units in the same form as the equation. We're going to score them out, so the moles per decimeters cubed bit, that will kind of cancel out. We're left with an s to minus 1 on the top there, and we've got moles per dm cubed at the bottom. When we shift that up, we invert it, so we put mole to the minus 1, dm to the 3 because we're moving it to the top. So that leaves us with mole to the minus 1, dm3, so basically we're just kind of swapping these top numbers at the top. That's already on the top line, so that remains the same. That's s to the minus 1. And that's your units of K. So just make sure you're working out your units correctly. Okay, really, really important because you get a mark for that. Okay, so we're going to calculate initial rate from a graph. Okay, so initial rate, obviously, when we looked at, say, reactions, when we looked at the curved reaction, and we could find out the rate at a specific point in time. And that's fine. But with curved graphs, the rate is changing all the time, all the way through. So it's really handy as scientists to keep things comparable, is to kind of pick a fixed point in time. And here we're going to look at something called an initial rate method. Now, initial rate can be found using a gradient of a tangent too. Okay, so now initial rate, as it kind of expects, is basically the rate right at the start of the reaction. So basically it's probably the fastest point at which this reaction is going to happen, because you've got loads of reagent there that haven't reacted. You've literally just mixed it. We're looking at the rate of reaction right at the start of that point there. So what we're going to do is, just like the slides before, we're going to take the gradient of the tangent, but the initial rate, we're going to take it at 0 minutes. Okay, so the tangent at 0 minutes is going to be that. Okay, so that's going to be at 0 minutes. And so therefore the gradient, again, is the change in y over change in x. So here you can see we've got a change in y of 1.7, a change in x of 1, and then that's going to give us a gradient of 1.7 grams per minute. So you're going to find later on, later on when we look at different tables, a lot of the information we're going to be providing is initial rate. We've got initial rate method, a way in which you can measure the rate of reaction right at the start of the reaction. So let's have a look at this. Actually, it's kind of see. I'm just predicting what's happening next. So yes, the initial rates method, it's a really good way of actually working out the rate equation for reaction. So we can use the data from an experiment to work out what the rate equation could be. So let's say we want to work out the rate equation as we've just seen before. So the rate equals K, and then the concentration of your substances. So let's say we've got this equation, A plus B plus C will give D plus E. Okay, we can only work out the rate of equation by actually conducting an experiment. We can't just look at that, because this is why I've deliberately picked a generic example, because you can't look at that and say, B second order, A is first, and C 0. You just can't. You don't have a clue. So, picking a generic equation, a kind of arbitrary equation with just random letters in, just detaches that kind of temptation to do that. Okay, and this is why I've done that deliberately. So what we have to do when we're looking at this, or want to work this out, then we've got to repeat the experiment several times, but we're changing the concentrations of A, B, and C one at a time for each experiment. So what we're going to try and do is we're going to say, keep B and C the same, but change the concentration of A. We're going to run the experiment, take some data, and then see what happens. Then we're going to kind of put A back to where it was before. We're going to change B, but keep C the same. Then run the experiment together. So we're going to have a lot of data being taken from kind of loads of mini experiments. What we're trying to do is we're trying to isolate and see what impact does each one of these chemicals, A, B, or C, have on the rate of reaction. And so if we changed all of them at once, we wouldn't have a clue which one is actually going to impact the rate of reaction. So we need to work out the initial rate for each experiment, and obviously we calculate this using the graph that we've seen before. And then what we do is we record the concentrations of reactants used for each experiment and their initial rates in a table. Okay, and then from this data, we can then use that to work out the orders, and then we can then work out what the rate equation is once we've got the orders. So that's the method, that's the approach that we're going to take, and obviously we're going to see this on the next slide as well. Okay, so like I said, it's a great way of working out a rate equation. So let's have a look at this one. We're now going to kind of bring in a real example here. Okay, so we've got some experimental data for this reaction. So we've got 2 lots of NO, that's nitrogen monoxide, reacted with chlorine to form NOCl. And we're going to give the rate equation, well, we need to find out what the rate equation is and calculate the initial rate for experiment 4. Okay, so basically this is the data we've taken. So we've got the concentrations of NO and Cl2 recorded here. So this is experiment 1, and this is the rate here. Experiment 2, you can see we've kept NO the same, but we've changed the concentration of chlorine, so that's increased, and that's the impact it had on rate. And then experiment 3, we've got 0.8, so obviously increased that, but we've kept and we've decreased the chlorine back to where it was before, so that's obviously the same, and this is the impact it's had on rate. Obviously the last one we've changed it again, and we didn't work out what the rate is for that. Now you might think, well, that's not a very good person who's actually kind of done this practical, why would you miss that out? Obviously this is just for the exam, they want you to kind of work out different elements here. Okay, so anyway, this is the data we've got. So we need to work out the rate equation, and we need to calculate what the initial rate is for experiment 4. So when you get a question like this, okay, the first thing we need to do is work out order with respect to NO. Okay, now ideally we need to compare experiments where the concentration of NO is changing and the concentration of chlorine is constant, okay, is remaining the same. So obviously we've got the top one and experiment 3. So that is where the concentration of chlorine is obviously the same. That isn't changing. So any changes to rate we know has got to be because of the changes to the concentration of NO. Now we can see that rate is changing. So we know that the concentration of NO, or change in the concentration, does have an effect on rate. That's the first thing we can say. But what we've got to do is measure that, is quantify that. So experiments 1 and 3, we can see the concentration of NO is actually quadrupled, so it's multiplied by 4, and the initial rate has quadrupled as well. So what that tells us is that the order with respect to NO is first order, because if we quadruple NO with quadrupled rate, it's proportionate. So there's our first response there, first answer. Tick. Right, so secondly, obviously we need to work out the order with respect to Cl2 as well. Again, we need to compare the experiments where chlorine is changing, but NO remains constant. So we've got 1 and 2. Okay, so NO is remaining the same, so that's 0.2, but the amount of chlorine is increasing as well. Now we can see here that rate is changing, so we can see that chlorine must have an effect on rate of reaction, because it is actually having an impact. Concentration of NO isn't changing here. So we can see here chlorine has trebled, so the concentration of chlorine has trebled, and the initial rate has trebled as well. So the order with respect to chlorine, Cl2, is first order as well. Okay, so now we can then say, right, the rate equation is rate equals K, concentration of NO and concentration of Cl2. So that's the first bit done. We've worked out what the rate equation is. And when you get questions like this and they're asking you to work out, say, a blank space in the table here, the first thing I would probably do is try and work out what this is first, because this is going to give you a lot of options in terms of working this out. Now, clearly, we want to work out what the initial rate is for experiment 4. For some reason, the data is missing. So you probably might have spotted it, that we're going to use this rate equation here to work out what the rate is at this point here for reaction 4. Okay, so let's bring that table back. There's our rate equation there. So really simply, what we're going to do is we just need to calculate K. Okay, so we need to calculate what this is first. So we know that, because we've got this data here. So we know it's 0.5 and 0.5, but we don't know what K is here. Now, remember that K is the same value for all experiments in this table here, because assuming that the temperature is the same, so which is a fair assumption to make, and that will be the case as well. So all this is run at the same temperature. So what we're going to do is just pick any experiment, any one of these with all the data complete to work out what K is. So let's go for the top one, just because it's the top one. So we're going to use the data in experiment 1, and we're going to rearrange this equation to work out what K is first. Okay, so K equals rate divided by concentration of NaCl2. Put your numbers in, okay, that's in the table, 0.2, 0.1, 0.63, and that gives us a value of K of 31.5 mol to the minus 1 dm cubed S to the minus 1. Okay, so now we've got K, we can kind of bank that, and then we can use this number here alongside these two numbers here to work out what the rate is for experiment 4. So experiment 4 is rate equals K concentration of NO and Cl2. So you're going to use the number we've just worked out here, multiply that by 0.5 and 0.5 at the bottom. They're both first order, and so therefore the rate here, this number here, should be 7.88 moles per decimeters cubed per second. And that's basically how you work it out. So there's a lot of steps involved there, but hopefully it follows a logical process. So you work out your rate equation, try and aim to achieve to get this first, because this is massively going to help you get this rate equation, because you can use it to work out loads of different things from it, as you can see. Okay, we're going to look at a tricky one here, okay, and they might throw in a kind of a bit of a curveball with this, but sometimes the rate tables don't have a substance where the concentration remains constant, and it's really annoying. It's really annoying. And practically, you wouldn't do this. You would always set up an experiment where you're keeping one concentration, one of them the same, and changing the other one. But you know, this is not a real exam situation, not a real practical situation, and the examiners want to test your knowledge. They want to really test to see what you're going to do here. So we've got a reaction occurs between A and B, okay, and the experiment was repeated 3 times, varying the concentrations of A and B. Now what we're going to have to do is give the rate equation for this reaction using the data below, okay, so we're basically working out what this rate equation could be. Now we've got 3 experiments here, and you can see that we've got experiment 1, initial rate concentration of A and B, and the rate of reaction, and we've got it for 2 and 3. But what you can see here is that where concentration of A is never constant, okay? Every single experiment we've changed it. It's constant for B in 1 and 2, but not for A. That poses a problem because it's really difficult for us to isolate what impact A is actually having on rate. So we're going to have to do a little bit of extra work with this one to work this out. So first of all, we need to work out order with respect to A. Now, like I say, ideally we need to compare experiments where concentration of A is changing and B is constant. But there we are. Okay, so we can work out concentration of A because we know B is obviously the same. So A has trebled here. Okay, and the initial rate has actually increased by 9. So we know that in this experiment here, the order with respect to A is second order. Okay, so it's increased disproportionately. So that's fine. Okay, secondly, obviously we need to work out the order with respect to B. Now this is tricky, as I mentioned before, because A changes in each experiment. So what we're going to do here, okay, is we're going to add another column at the end, okay, and this is going to show what the rate would be. And it's like a hypothetical one. Now you might have a different method of doing this. This is one particular way of doing it. I believe in trying to keep things as simple as you possibly can and kind of record things so you know where you stand. You might have another method and you might think it's fine. This is just one way in which you can do it though. Okay, I appreciate there's other people might have different ways of doing it. But if we add another column at the end, and we're going to show what the rate would be if we only changed A. Okay, so we're going to look at this here. So looking at experiments 2 and 3, we can see the concentration of A doubles. Okay, so we know that rate must quadruple, as we know at second order. We've just worked out here that with respect to A, it is second order. So we know the impact of A is going to leave you with 15.1 times by 10 to the minus 3. Okay, we know it's second order. Now, we're not saying it's definitely this. We're just putting in a figure here of something that we do know. Okay, and at least it's given us a foot in the door. Okay, we've got that start. Finally, okay, if we look at what the actual rate has come out as, the actual rate was actually 7.56 times by 10 to the minus 3. So we know because these numbers don't match, we know that B must have some effect on rate. It's got to. Okay. Now what we're going to do here is basically want to look at is, well, what's the difference? This is what it would be if it was just looking at A. What impact has B had? So we can see here there is a difference on the rates. So B does have an effect. We can see it's about half. Okay, about half the amount, and this is caused by halving B, and we can see here that B is halved in terms of the concentration, and so has the rate. The rate is halved from the hypothetical value. So what we can say is that B is actually first order with respect to B. And then finally, obviously, we can put in our rate equation and say, right, well, the rate is K, okay, concentration of A squared, and the concentration of B is obviously first order. Okay, so just be really, really careful with ones like this. Okay, so they probably might put this in, actually, to be honest, or something similar, because it just gets you to think a little bit more. It really tests your understanding of rate and initial rate methods. Okay, so we can use obviously graphs. We talked about that's obviously tables of data, and obviously we can plot any of these reactions on graphs as well. And actually we can use the graphs or rate concentration graphs to help us identify the order of a reaction. So a rate concentration graph is obviously created by knowing the rate, and obviously the rate is found by taking the gradient at various points on a concentration time graph. I don't want you to get these two mixed up, okay? You've got rate concentration, okay, and you've got concentration time graphs. So let's have a look. So we've got the rate on a straight line graph is constant. Okay, so the rate concentration graph shows a horizontal line, and changing the concentration doesn't actually change the rate, and so this is zero order. So you can see here we've got a concentration time graph. So this is what you'd probably plot directly from experiment, and you can see that as we change, as time goes on, the concentration is obviously decreasing over time. From that, we can monitor the rate at different points on this graph. The rate isn't changing across there because it's a straight line graph, but we can measure the rate across these different points here, and we can plot another graph and say we've got rate and concentration of A, and we can plot using the rate here. And anything which provides a straight line like that, in other words, changes in the concentration has no impact on rate, we can say it's zero order. Okay, so if we look at another one, so here we've got concentration is decreasing faster initially and then slowing down over time. Is effectively, if we take the gradient effectively of various points across this line here, then the rate is actually changing. It's obviously faster here, and then it's obviously slowing down, over this period of time. So we can see that the rate, when we plot this on a graph of rate concentration, we get a straight diagonal line upwards. And when we see this on this type of graph, it's first order. And finally, second order is very similar to the first order, except it's disproportionate. And we can see here that if we plot the gradient at each one of these points, i.e. we calculate the rate, and then we take the various rates across this line here and plot them against concentration of A, we can get this nice curved graph going upwards, and this obviously represents second order. You need to be aware of the shapes of these graphs. Look at the axes, don't get them confused, and you need to be able to identify if something zero, first or second order. Okay, really, really important. But look at the actual, the titles the axes here, because that's going to obviously see the graphs are different. So just don't get confused with these two different graphs. This you normally derive straight from experiment. This is derived from taking the rate of each one of these graphs and plotting it against the concentration of the reactant. Okay, so we're going to look at another concept, and again, if you do physics, you might be familiar with this. This is half-life. So half-life, or T-half, is basically the time it takes for half of the reactant to be used up. Now, if you study physics, you might have seen this in terms of radiation, so half-life of, say, a radioactive substance. So half-life, it can be calculated using a concentration time graph. Okay, so this is the graph that you take straight from experimental data. So we've got a graph here, and this is going to show the decomposition of hydrogen peroxide over time. Okay, as you can see on the axes. So the graph shows, if we look on here, it takes 200 seconds, okay, as you can see at the bottom there, for half the hydrogen peroxide to decompose. So from this point here to here, that's half of it to decompose. It took 200 seconds to do that. Okay, so that's dropped from 2.6 to 1.3. So we can pick any concentration value on the graph and find out how long it takes for it to halve. So let's have a look. There's another one. Okay, so we're going to say this is going to halve again. How long did it take for that to happen? So that one was another 200 seconds, okay, that it took. So we can see that when we halve the concentration, how long did it take? Now on this graph here, we can see that the half-life is actually remaining constant. The length of time it's taken for half of the reactant to be used up is remaining the same. So we can say, we can actually say that obviously the half-life remains constant here. So we can calculate obviously the rate constant K from half-life, which is T a half, and the equation is K equals 0.693, okay, divided by T and a half. Okay, so in this example, it's going to be K is 0.693 divided by 200, because that's obviously a half-life, and obviously that gives you 0.00347. Okay, so make sure that obviously you're aware of how to actually work that out. Okay, so this is how you work out the value of K. Okay, there we are, K. Right, too many Ks. So, yeah, so that's basically how you work it out. So that's the value of K there. So we use this specific equation here, okay, this one here, to work that out. Not too bad. Okay, so actually these concentration time graphs, as we've seen before, they can help us identify the order of a reaction. So concentration time, anything where we get a diagonal straight line downwards is zero order. So the rate on a straight line graph is constant. Changing that concentration isn't actually changing the shape of that curve. So that doesn't change. And half-life decreases as we go down. There we are. Okay, so you can see the half-life as we go across that graph, something with zero order, it's decreasing over time. So let's have a look at a first order graph. So this is a shallow curve. It changes in equal amounts. It's all proportionate. So changing the concentration of A, for example, in this example, will change the rate by the same amount. So it's all proportionate. And the half-life is constant. So let's have a look. There we are. So the difference between them is the same. It's equal. Okay, so whenever you see a concentration time graph like this, and again, they might be expecting you to look at this graph here or comment on half-life and how half-life links with order of reaction. If the half-life is equal, just like we've seen in the other example, then we know it's first order. Now, if we look at second order, okay, so it's a steeper curve. It changes, obviously rate changes in unequal amounts, so it's not directly proportional to. Then changing the concentration changes the rate squared, and actually half-life increases. There we are. So you can see the half-life is increasing over time, and that's a classic example of a reaction that is second order. Okay, so we're going to kind of step away from that, and we're going to look at something called a rate determining step. Now, this is a bit of a strange one. Hopefully you kind of understand this. I'll try and make it as clear as I possibly can. But the rate determining step is the slowest step in a multi-step reaction. Now, a lot of reactions actually don't just go via one step, they go via a few different steps. Some of them steps can be really quick and rapid, some can be slow. Now, what you're expected to do is to be able to look at some of these multi-step reactions and identify maybe what the rate determining step is, or be able to have some discussion around it. So let's have a look at some examples here. So like I say, most reactions kind of occur via multiple different steps, and out of these, one of them is what we call a rate determining step, or at least one of them. And the whole reaction rate, for the whole reaction, depends on how quick this rate determining step is. Okay, so now I'm going to kind of give you a bit of a warning with this. Now you're going to see some kind of pictures of my my baking attempt, and I'm going to try and use an analogy here to try and explain it, because I think this can be quite difficult without some form of analogy. It becomes quite abstract, so I'm going to try and use a baking analogy to kind of help this one along. Okay, so so we've got we're going to make a Victoria sponge. Okay, so baking a Victoria sponge can be seen as a multi-step process. Okay, so we don't just get the ingredients, chuck them together, and hey presto, you've got a cake. You've got different steps involved to making it. So step 1 is obviously to gather the ingredients, so that'll take about 10 minutes. Step 2 is to mix all the ingredients together, about 5 minutes. I appreciate some people might be saying, hang on, it might take longer than that. Yeah, it might do. This is just to illustrate something, okay? Bake in the oven and cool afterwards. So baking in the oven and cooling it as well, so leaving it on the cooling rack, is 1 hour and 30, so that takes quite a while. And then step 4 is dusting with icing, putting your filling in, about 5 minutes. Okay, so this is the steps in which we can make something from it. Okay, this is no different to a reaction, to a chemical reaction. So we can see here that the cake takes 1 hour and 50 in total to make. So that's the total amount of time to make the whole thing. The rate determining step is step 3, because obviously that's the slowest step. So baking in the oven and cooling afterwards takes the longest amount of time out of any of the other steps. So if we're to reduce the overall time significantly, okay, we need to speed up step 3. Okay, that's going to be the key thing. So if we're in the business to make as Victoria sponges as quickly as we possibly can, then we need to look at the method in which we manufacture this or make this. And clearly the bit which takes the longest amount of time is step 3. So what we can do to speed that bit up, we can put it in the fridge. We can use a fan oven, for example, so that might take obviously speed up the cooking process. So there are things we can do to try and overall speed that up. But us kind of trying to speed these elements up, we could try that, but it's not really going to have that much of an impact on the overall time it takes to make the cake. So in chemical reactions, we have a similar problem, except obviously to speed up a step, we can't just use a fan-assisted oven or use a fridge. We've got to use a catalyst, or we can change the temperature. So we can put other things in place to try and speed up these multi-step reactions. Now remember what I said earlier about the rate equation. So reactants that appear in the rate equation will affect the rate of reaction. So any reactant which has 0 order does not appear in the rate equation. Okay, so therefore it doesn't have any impact on the overall rate. It has very little. So these reactants or substances derived from them, okay, must appear in the rate determining step. Okay, so any which are kind of in the rate determining step, they've got to appear, or the kind of derivatives of them must appear in the rate equation. Okay, substances that are not in the rate equation will not be in the rate determining step. I can't make that any clearer. Okay, and you'll see some examples in a moment and see where this fits in. Okay, just be aware as well, it's not just reactants that can appear in the rate equation. Catalysts can appear in there as well. So you might see A plus B forming C plus D, and you might see the letter F in there, and you think, well, where's F come from? But if F's in the rate equation and it's not a reactant, then it'll be a catalyst. Okay, so just be aware of that you might have like a phantom chemical in there that's not actually in the equation. Okay, so like I said, we can work out the rate equation from a multi-step reaction. So here we're going to deduce the rate equation for the following generic reaction steps. So we've got step 1, which is A plus B will form 2 lots of C, which is a fast reaction. Step 2 is 2C will produce D, and that's slow. And then step 3 is D and E will then react together, so that's D that was produced in the previous step. So D and E will produce F and G, and that's a fast step. So the overall equation for this reaction is A plus B plus E will form F plus G. Okay, so this is the overall equation. Again, I've just detached it from any kind of particular chemical. So the first thing we need to do is look at these and say, right, well, we know the rate determinant step is the slowest step in a multi-step reaction. So in this case, it is step 2. Okay, so this is the slowest step. So one of the reactants, as we can see here, is C in that rate determinant step. So that must appear in the rate equation. Okay, it's got to. Now, if you notice, there's a 2 next to it, and this tells us that the power is actually 2. So we know it's second order with respect to C. Excuse me. So we know we can do this with multi-step reactions. So C, okay, is an intermediate, and this is formed from or derived from A and B. Okay, and so for this reason, both A and B must be in the rate equation too, because we wouldn't have C in the first place if it wasn't for A and B. So clearly A and B will have an impact as well on the overall rate of equation. So there are only one of A and one of B, so it's first order with respect to A and B in this case. So the rate equation simply can be deduced as rate equals K, A, B, and then C squared, and that is effectively your rate equation. So you can see that C, though, is not actually a reactant. Okay, you can see the overall equation, C doesn't appear there at all. So C is a catalyst in this case. Okay, so obviously this is an example of autocatalysis, which actually you'll see later on in this topic. So it's not topic 15. Obviously we'll get that changed, but it's actually this topic here, so you'll see a bit of autocatalysis later. You'll see a little bit as well in transition metals as well, so we'll look at that as well. But actually, you're in for a treat. So this was actually done in the old syllabus as well, so I'll get that changed. Okay, so the rate determinant step can be found from the rate equation. So we're going to kind of do it backwards this time. So we're going to deduce the rate equation for the following reaction steps. So you've got step 1, which is NO plus NO will form N2O2. And step 2 is N2O2 plus O2 will give 2NO2. There's a lot of NOs and 2s. The overall rate equation here is rate equals K, the concentration of NO squared, and the concentration of oxygen, which is O2. Okay, so we've been given the rate equation. So what we're being asked to do here is to work out what the rate determining step is. We haven't actually been told which one's fast or which one's slow. We've been given the rate equation instead. So the first thing to notice is the ratio of molecules that we're looking for. So in that rate equation, we're looking for 2 lots of NO, okay, and 1 lot of O2. And looking at the reaction steps, there isn't one single step with this ratio in there. Okay, so this is a little bit like chemical bingo. Okay, it's dead quick, this method I'm going to show you here. I know a lot of people look at this and think, I don't have a clue what it's asking us to do, and they're looking for reactions with these ratios in there. It isn't about that. So remember, the rate determinant step must have at least one of these substances in here, but it's also the chemicals that make these as well. So we're going to start from step 1. Okay, when you're faced with this and there isn't any single reaction here, we're going to start from step 1. So this is what we're looking for. We're looking for 2 lots of NO and 1O2. So we're going to start from right at the top when you face this, right from the top, and just start scoring them off and keep scoring until you've got everything, until you've hit bingo, effectively. So we're going to score off the molecules or atoms needed to match this ratio here. So we're looking for 2NO and 1O2. And we're going to stop once we've counted them all. Okay, so are you ready? So step 1, we have 2 lots of NO. Okay, we're going to score them off. So we're going to go 1, 2. Okay, so we've got rid of them. So that's the first thing. We're still looking for an oxygen though. Okay, so we need to keep going. So this is not the rate determining step. So we continue to step 2. There we are. So we score them off. Okay, we need to go to step 2. Step 2, we have our oxygen there. Okay, there it is. And we've now accounted for all of our molecules. And at this point, we stop. Okay, bingo, we've got everything. And effectively, the point at which you stop, the first opportunity when you've scored everything off, that step is your rate determining step. It is that straightforward. Okay, I know a lot of people look at this and think, I don't really have a clue what I'm looking for. You're just literally scoring them off, and the last step that you're at, even if this is 20 steps, you're not going to get that. But even if it's 20 steps, and you had about 10 different molecules in the rate equation, then you just basically keep going. You keep scoring them off until you've scored off the last one, and that is the equation that is your rate determinant step. Dead easy. It's just so quick. Okay, but hopefully, and you might have a different method of doing it. I just personally think this is the most simplest and quickest way of trying to deduce your rate determinant step. Right. Okay, so the reaction mechanism, this can be found from the rate determining step as well. So the following reaction can occur via 2 potential mechanisms here. So we've got this molecule here, okay? We've got OH minus, and we're going to form obviously this alcohol here plus Br minus. So this is the reaction we're going to be looking at. They could give you all sorts of exotic equations here. It doesn't really matter, okay? It's all you're looking for is rate determining steps, as we've just seen before. So don't be kind of clouded by what they've got here. So it can proceed via mechanism 1, which is basically just all in one go. Or it can proceed via mechanism 2, whereby it actually proceeds via 2 steps. So we've got this one which is slow, this one which is fast. Now, the reaction is found to have the following rate equation. So obviously you were provided with this, or you would have been able to work it out. So rate equals K, and we've got CH3, 3, CBr. Okay, which mechanism is likely to be correct? Is it going to be mechanism 1, or is it going to be mechanism 2? So we've got the rate equation, so let's have a look. So we've got a strong CR bond. So start again. We've got a strong CBr bond, okay, between them, and this is broken. So this is the slow process, okay. So obviously to break that CR bond, it takes a lot more energy to break that up than to join a negative and a positive ion together. So this is why this step is a slow process. And there's a good chance of a collision, obviously, between a positive and a negative ion, and this is why this one is a fast step. So it's very likely for these to happen. That's more likely; they're more likely to collide than that is to break. Okay, because that takes energy to do that, and this is why this top one is slow. So the rate equation tells us that only CH3 CBr can appear in the rate determinant step. Remember, okay. So what we're looking for is, can we have, or can we see a mechanism where only that appears first? That's the priority, okay? Nothing else, just that. Mechanism 1 shows CH3 CBr, but it also shows OH minus ions. Mechanism 2 does only show CH3 CBr. So therefore, this suggests that the reaction is likely to proceed via mechanism 2, because the rate determining step here, that one, matches the ratio of elements in the rate equation. So in this instance, it's likely to proceed via mechanism 2. So we're just looking for some certain things here. These notes here are just to kind of explain why this might be slow and this might be fast, because you might look at that and think, well, how do they know that's slow? So it's looking at some, applying some common chemical knowledge that we've seen before to try and explain why this might be slow and why this might be fast. Okay, so we're going to look at some different types of catalysts. Again, you would have seen some of these already in terms of the different types of catalysts, homogeneous, heterogeneous. However, what you do need to be aware of is some specific examples for year two. Okay, so as you might have seen before in year one, catalysts can be homogeneous or heterogeneous. And catalysts are important, obviously, in rate of reaction because they help speed up the rate of reaction. So you'll remember heterogeneous catalysts are based in a different phase from the reactants. Okay, so different chemical state, different states. So there might be solids, liquids, gases. So a classic example is the Haber process, and this is where you've got nitrogen and hydrogen. These are obviously all gases. You're producing ammonia, which is a gas, and we use a solid ion catalyst for this. Now, obviously, that's in a different phase to these reactants here, so therefore it is heterogeneous. Now, with these catalysts, if we increase the surface area of these catalysts, then we will increase the rate of reaction. There's basically more sites in which molecules can adsorb to, and we'll look at the mechanisms of that as well. And that obviously allows it to react, or allows reactions to happen much more quickly. Homogeneous catalysts. So these are in the same phase of the reactants, and generally they are found in aqueous solutions. So, for example, if you've made esters in year one, for example, you would have added sulfuric acid in there as a catalyst. So esters and sulfuric acids are all aqueous solutions, so therefore they're all the same phase. So it's still a catalyst, but it's not a solid catalyst as we've seen with the Haber process. Now, as you'll see in a moment, these form intermediate species. Okay, and these by reactants obviously combine them with the catalyst, and they react to form the products, and then the catalyst is then regenerated again. So the kind of catalyst is a little bit more hands-on within the reaction. It actually breaks apart, it reacts itself with a reagent, and then is reformed later on. Whereas with heterogeneous catalysts, it's normally just a solid base for chemicals to adsorb to, and then break apart afterwards. So it's not actually kind of chemically changing in some senses. So let's look at heterogeneous catalysts first. And we need to know, for year two, we need to understand the kind of mechanics of how a heterogeneous catalyst works. So substances, they adsorb to the surface of a heterogeneous catalyst. Now, adsorb is really important. It's with a D. It's very different to absorb. So absorb with a B means to kind of like a sponge, it absorbs water. Adsorb means it adds to the surface. Okay, so it sticks to the surface, not integrated within the actual catalyst. So they bond to the surface of the catalyst. We call this adsorption. It's not a spelling mistake. So the bonds in the reactants weaken and they break to form radicals. Okay, so the atoms and molecules, obviously they're with an unpaired electron, if you can remember from year one chemistry, so there's a bit of a kind of nod to that as well. And these radicals then react with others to make new substances. Obviously, remember, radicals are quite reactive. So new molecules are then released from the surface of the catalyst, and this is called desorption. That's where it leaves the surface of the catalyst. So you need to know a particular reaction, which is the Haber process, and we're going to look at the formation of ammonia using ion catalyst in the Haber process here. So here's our ion catalyst surface. Okay, so it's a heterogeneous catalyst, so it's metal, and we're going to add some of the molecules here. There they are. Okay, so they're going to add to this reaction, okay, to this catalyst. So we've got forces that are kind of involved. You've got nitrogen here, N2, and you've got 3 lots of H2 here. So they adsorb to the surface. So then what happens is obviously they react. We have a reaction, so these will kind of drift across. They will form ammonia molecules out of these atoms here, and they will desorb and break away from the catalyst surface, and that obviously leaves the surface free for further reaction to happen on. So obviously this can be used, again, the same principle can be applied for the removal of oxides of nitrogen from car exhaust gases. It's exactly the same, except we use normally a platinum, palladium and iridium catalyst. It's a mixture of different precious metals in an exhaust. The same principle applies, whereby you've got nitrogen, removal of oxides of nitrogen from car exhausts and carbon monoxide as well. That's passed over these solid catalysts, and then out pops carbon dioxide instead, okay, and nitrogen gas. So you're getting two different products that are being formed. So that's basically a heterogeneous catalyst. Now, if we look at heterogeneous catalysts, the issue with these is they can be poisoned by impurities, so they don't last for life once you put them in. That'd be brilliant if you could do that. It would save an absolute fortune. But impurities can bind to the surface of a catalyst, and it can block some of the active sites for reactants to actually adsorb to. And any impurity that does this, we call this catalytic poisoning. Okay, so it's where the catalyst is less effective. Okay, so the catalysts, especially heterogeneous catalysts, over time they may need to be replaced because the poisoning effectively renders the catalyst redundant. And actually, this is one of the reasons why when you take your car, well, some of you may not drive, but you may understand that with some cars in the UK, well, most cars over the age of 3 years old, I think it is, you have to take them for an MOT test, and one of the tests for an MOT is emissions, and they basically monitor the gases that come out of the back of an exhaust if it's a combustion engine, and if the emissions are too high, then there's likely to be an issue either within the engine itself, it's not burning the fuel properly, or if it's an older car, the catalyst may have been poisoned and actually the catalyst isn't doing its job, in which case you need a new catalytic converter, which would be quite expensive, I'd imagine. But and this is why catalysts do get poisoned, and as a result, cars in particular need to be tested to make sure their emissions coming out of the exhaust are not too high that they're actually causing because they're toxic. You shouldn't really be breathing these in. So, looking at the Haber process, though, because again, this is a specific example you need to know, nitrogen and hydrogen produces obviously ammonia. Hydrogen is made from methane, okay? So that's how you make the hydrogen in the first place. Now, the problem is methane contains sulfur impurities that's contained in that. So what you can get within the catalyst, or the catalytic poisoning, is that any sulfur that is not removed will effectively adsorb to the surface, and this will form iron sulfide. And obviously this is now blocked, this will not break away, and this site is now kind of redundant. No other reagents can attach to this. And if you imagine this catalyst surface has got loads of these dotted all over the place, then obviously the catalyst doesn't become as effective. So a poison catalyst, obviously less product is made, it needs to be replaced, or it can be cleaned if it's cost effective to do so. It increases the cost of chemical processing. So it's really important that obviously as scientists, if we can develop catalysts that can remove this process here, or try and resist it, then that'll be ideal. And obviously this is why there's still huge areas of chemical research in particular of developing much more advanced catalysts that can potentially clean themselves, so through chemical reactions. So useful. Okay, so looking at, and again this is just a nod to the year 1 chemistry as well, we're going to look at the Maxwell-Boltzmann distribution. Again, if you're looking at this thinking I haven't a clue what a Maxwell-Boltzmann distribution is, please look at the year 1 video. Okay, I'll go into it in a lot more detail there. I'm not going to go into it too much for this purpose here, so I encourage you to look at reaction kinetics for the year 1 topic. So this is the Maxwell-Boltzmann distribution. But effectively, a catalyst will lower the activation energy, so a heterogeneous catalyst. So it means you've got more particles with energy greater than the activation energy. And obviously, if we look at the energy profile diagram for this type of reaction, so you've got reactants, you've got products. So this is the profile that reaction could follow if it didn't have a catalyst in there. Obviously, we throw a catalyst in there and that reduces the activation energy, and less energy is required for this reaction to occur, as you can see on there. So that's the impact the heterogeneous catalyst has. So obviously this applies to homogeneous catalysts as well. So in terms of this Maxwell-Boltzmann distribution, there's no difference. This applies to homogeneous. The energy profile diagram is different for homogeneous catalysts, as we'll see later on, but the Maxwell-Boltzmann distribution is just the same. There's no different there. Okay, so finally, let's look at a homogeneous catalyst, and obviously these kind of behave in a mechanically so I suppose the kinetics of this is different. So homogeneous catalysts, they actually combine with reactants to form an intermediate species, and then that reacts to form products, and the catalyst is then reformed back again. That's really important. Catalysts are never used up. They're always reformed. They may react with the chemicals, but they're always remade at the end. So as we mentioned before, homogeneous or heterogeneous catalysts, they do the same job. They lower the activation energy that's required for this reaction to occur. So they're always reformed, as I mentioned before, and we need to look at a specific example. So here we're going to look at the oxidation of iodines using peroxide disulfate as the catalyst. So S2O8 2-. Okay, now you do need to know this specific reaction. So the reaction uncatalyzed is really slow. Okay, so what we're trying to do here is we're trying to react negatively charged ions together, and that's a bit like putting a north and a north of a magnet together, of powerful magnets. They just don't want to be near each other. So it's the same with these chemicals here. So we've got a really high activation energy because we're trying to force S2O8 2- ions and I- ions to react together. There's just no chance. They look at them, they've got two negative charges. They're going to kind of look at each other with kind of some level of disgust and say, well, I'm not going to go anywhere near you. So we need effectively a catalyst to kind of mediate or kind of trick them into reacting together. And the catalyst here is Fe2+. Okay, so this is going to be the kind of helper, I suppose. And this lowers the activation energy, it speeds up the reaction. We need to know the reactions to do this. So the first part is the reduction of peroxidase. Okay, so peroxidase reacts with Fe2+. More than happy to react. They're oppositely charged, no issues there. So that reacts and you form Fe3+, so the Fe is oxidized, as you can see there, and the peroxidase sulfate, S2O8, is reduced to 2 molecules of SO4 2-. Okay, so really, really important. So then this Fe3+ is an intermediate. Obviously, that's not the catalyst, is Fe2+. It's actually reacted to form Fe3+. So this, it then goes off to react with the I-. So it runs off, goes to the I-, and then reacts with the I-. So the Fe3+ is reduced back down to where it was before. So the catalyst is reformed at this point, which is Fe2+, and we form I2. Okay, so we form iodine. So effectively what we've done is we've produced the products that we need. We've got our I2, there it is, and we've got SO4 2-. There it is. But we've done it in a kind of proxy way. So the ion 2 is kind of got itself involved with the reaction and has reformed itself. This Fe2+ will then go and repeat this process. So we've actually formed the product, and if it wasn't for the Fe2+, none of this would have happened. So we can test for this. Obviously, we know that this reaction actually proceeds because we can use starch solution. And if we add starch to this reaction and iodine is present, then we get this black-blue colour that's formed as well. So we can actually see this reaction happen. Okay, so like I said, the catalyst reduces the activation energy required for the reaction to occur. Okay, so these homogeneous catalysts can combine. So let's have a look at another example. So this is an oxidation of sulfur dioxide, so SO2, in the atmosphere to sulfur trioxide, and we're going to use NO2 as the catalyst here. So sulfur dioxide, this can be released in the atmosphere through the burning of fossil fuels, as we've seen in year 1 topics. Previously we know about the impacts on the environment. Obviously this leads to acid rain because it makes sulfuric acid, and obviously we need to know how this is made as well. So first of all, the sulfur dioxide reacts with the nitrogen dioxide, which is another pollutant in the atmosphere, and obviously this forms sulfur trioxide, as we can see here. And the second step is the nitrogen monoxide intermediate that's produced, so this bit here, okay, in the first part reacts with the O2 to reform NO2 again. Okay, so that's reformed again, and this proves that actually in this example here, NO2 is a catalyst. So just be aware, looking at these reactions here, make sure you can kind of identify or prove or demonstrate, that if a catalyst exists, a homogeneous catalyst exists, that you can actually identify it. Okay, and obviously the SO3 produced in the first step here reacts with water, and obviously that makes the sulfuric acid in the atmosphere, which leads to acid rain. So here we're just looking at an unknown reaction, I suppose, and we're able to describe why something is why something is a catalyst. Remember, catalysts may actually get involved with the reaction, but they're always reformed at the end. So if you're seeing something being remade that we had at the start, that's a catalyst. Okay, so that's all you're looking for. Okay, so let's have a look at the final bit really of this is looking at the energy profile diagram for homogeneous catalysts. Now, as we've seen earlier, they have this intermediate that's formed. So let's have a look at a normal reaction profile. So we can see you've got reactants and you've got products, and this is a chemical reaction with no catalyst that's actually attributed to it. And if we have a catalyst, a homogeneous catalyst, we actually have a kind of intermediate phase. So we've got this double bump, I suppose. So the first step here, overall, it reduces the activation energy. That's the first thing. So you've got more particles have enough energy to react. But we have the first step, as we've seen with the peroxidase sulfate reaction, you form that intermediate. So that's that first step there. And then you have this kind of second reaction with homogeneous equations where you have this second activation energy here. But the overall effect is that it's lower than what it would be if you didn't have that reaction there. So this just shows you the kind of the two-step reaction with homogeneous catalysts. So your intermediates are formed here. So that was the intermediates that we just talked about there, is in this kind of middle bit of the profile. And that's it. That's everything you need to know for reaction kinetics. Like I say, the full range of A-level videos, year 1 and year 2, is on Allery Chemistry. All I ask is you hit the subscribe button and just show your support for this project. That'll be absolutely fantastic. Also, these are available to purchase. You can use them as part of your revision notes. And you can scribble all of them, put them in your file, etc. They're available to purchase via the TES shop. If you just click on the link in the description box below, you'll be able to get a hold of them there. But that's it. Hope that's helpful. Bye bye.